The sun is high in the sky over Rocket Lab Launch Complex 1 on New Zealand's Mahia Peninsula, and Electron is standing tall on Pad B as we prepare to go to space for the 61st time in just under 20 minutes. My name is Muriel Baker and I'm a Senior Communications Manager here at Rocket Lab.
And I'm Matt Tier. I work on the avionics systems for Neutron. We're thrilled to have you join us once again to watch Electron take to the skies.
Today's launch is for our friends at iQPS, the Institute for Kyushu Pioneers of Space in Japan. They've named the mission The Lightning God Reigns, and if that name sounds familiar, it's because it follows on from our first launch for iQPS back in December 2023. Now that mission was called The Moon God Awakens, and it deployed a radar imaging satellite named Tsukuyomi-1. Today, it's the Lightning God's turn as we launch the first of 8 new missions for the Japanese Earth Imaging Company.
Across these 8 launches, Electron will expand iQPS's constellation of SAR satellites. These aim to provide persistent monitoring of Earth at fixed points every 10 minutes. Inside Electron's fairing is a single spacecraft, the QPS-SAR satellite, and it's headed to a 575-kilometre orbit. Let's hear more about their mission from the team at iQPS.
QPS-SAR project. The future begins in Kyushu. Maximum ground resolution of 46 centimeters. World-class image data enables observation of moving objects like cars and ships. QPS-SAR. A 100-kilogram class small SAR satellite. A constellation of 36 satellites will observe almost every location on Earth every 10 minutes on average. Unlike optical satellites, radar satellites can observe even through clouds and in darkness. The satellite processes observation data into images on board and transmits only the necessary images to the ground, delivering SAR images quickly. Using inter-satellite communication, even faster delivery is possible, aiming for about 10 minutes after observation. QPS-SAR data unveils a new world previously unseen. SAR satellites, unaffected by weather or time, can quickly assess disaster situations and confirm passable roads. Additionally, utilizing the radar's unique features, it can detect changes in infrastructure, such as roads and buildings, down to a few millimeters, allowing for pre-screening and repair of potentially hazardous areas. It is expected to be useful for managing large-scale infrastructure, capturing detailed information with high resolution. It can even contribute to reducing and eliminating illegal logging. Multiple satellites enable high-frequency observations, visualizing the movements of vehicles, ships, and planes, and allowing for fixed-point observations. It can detect sea ice even during nighttime or adverse weather conditions, providing information essential for the safe operation of vessels. Additionally, analyzing economic, weather, and other data using AI allows us to forecast urban and national economies, along with future trends. SAR images can be used to quickly create and frequently update 3D maps. By tracking changes in terrain and buildings, it provides accurate information essential for autonomous driving and other uses. The ultimate goal of the 36-satellite constellation is near real-time data services. By integrating SAR images into various applications, they become more convenient tools and are used routinely in everyday life. The QPS-SAR project aims to liberate the world from uncertainty and anxiety and sustain its daily life through satellites. Expand the possibilities of space and contribute to the development of the world. iQPS.
Right now, we are just over 14 minutes away from sending that QPS-SAR 9 satellite on its way to orbit. So for now, let's take a look at some of the numbers behind the launch vehicle that will take it there. So today's launch is our second for iQPS out of a total of 9 Electron missions that they have booked with us. It's also our third launch of the year so far, but our 61st Electron mission overall. And that includes our suborbital Electron variant HASTE. It will be our 57th liftoff from Launch Complex 1, since we've carried out 4 missions to date from Launch Complex 2 in Wallops, Virginia.
Each Electron has 10 Rutherford engines total. That's including 9 on the first stage and 1 on the second stage. So you'd probably think that means that we've sent 600 Rutherford engines to space, or 610 after today's flight, but that's where you'd be wrong. We've recovered and reflown one of those engines before, bringing the total number sent to space so far at 609. Since our first launch in 2017, we hit 50 launches faster than any other commercially developed rocket in history. We also deployed well over 200 satellites to orbit. This year, we have more than 20 missions booked on the manifest, so we're quickly adding to that deployment tally. No doubt you memorized all those figures and ready for the quiz at the end of today's broadcast.
But for now, let's give the numbers a rest and listen in for some very simple words instead. Go or no go? And that is the question our launch operators in mission and range control will be asked shortly by Launch Director Paula Teres-Sirolonga. They'll each report status on the various vehicle, ground and range systems they are responsible for, confirming whether or not they are clear to proceed with today's liftoff. So let's listen in for those calls now.
Control stations LD in mission core proceeding with go, no go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Vcon.
Vcon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
LDSAP.
LDSAP is go.
Go, no go sequence complete. We are T minus 11 minutes, 21 seconds and counting. We are go for terminal count auto sequence at T minus 10 minutes. From this time, the 3-word procedure is in effect.
That is go for launch from Mission Control, and we are proceeding with the count for an on-time liftoff at 1 p.m. local time today, just over 10 minutes from now. Now, today's mission has a 2-hour window, so should we need to adjust the T0 slightly for weather or any other reason, we have plenty of opportunities to do so.
While today's mission is all about sending something up to space, we recently completed a highly complex mission that did just the opposite. Our Pioneer spacecraft supported the re-entry of Varda's in-space manufacturing capsule, enabling it to land safely in South Australia. It was our second re-entry mission for Varda using our Pioneer spacecraft. And here's how we did it.
In-space manufacturing may sound like science fiction, but together, Rocket Lab and Varda Space Industries have made this a reality. Here's how. Across Varda's 4 missions, our Pioneer spacecraft will provide power, propulsion, communications, and attitude control in orbit. allowing Varda's capsule to leverage microgravity conditions to conduct in-space manufacturing and technology demonstrations. Our first mission for Varda was successfully completed in 2024, proving that the microgravity conditions in space can support pharmaceutical processing, delivering results that are challenging to replicate on the ground. Bringing the capsule back to Earth starts with a maneuver to transition the spacecraft from its 500-kilometer circular orbit to an elliptical one. We light up the spacecraft engine for a burn in the opposite direction to slow things down. This drops our perigee, or the point at which we pass closest to Earth, to 300 kilometers. A second engine burn will then raise the orbit's apogee, the point at which the spacecraft passes furthest from the Earth, all the way up to 900 kilometers. Rocket Lab and Varda operators in mission control will be monitoring this closely. As soon as the desired landing location on Earth lines up with the re-entry path for our spacecraft, it will be all systems go. The Pioneer spacecraft will perform a third engine burn of the 3D printed Curie engine to set the Varda capsule on its return trajectory to Earth. During that descent, a fourth burn can occur out of our line of sight to keep the mission on target if an adjustment to the trajectory is needed. Returning at hypersonic speeds at roughly 31,000 kilometers an hour, our spacecraft will release the Varda capsule at an approximate 470-kilometer altitude. This is the moment of success for Rocket Lab and our spacecraft. Then it's over to the Varda team to monitor the final re-entry, descent, landing, and recovery of the capsule once it reaches the ground. And just like that, from 900 kilometers above Earth to touchdown in South Australia, all in the space of just 15 minutes. The new era in space manufacturing continues.
Recently, our third Pioneer spacecraft for Varda was integrated and is shortly awaiting launch. So looking forward to another re-entry in the weeks to come.
Now, today's mission profile follows the standard launch sequence you've come to expect from orbital Electron missions. So after liftoff, Electron will move through max Q, main engine cutoff, stage separation, second stage ignition, fairing separation, and battery jettison before second engine cutoff and separation of the kick stage that carries the iQPS satellite. Now, that full sequence takes less than 9 minutes, and then we are in an elliptical transfer orbit. And from there, the kick stage and the payload coast around Earth for around 40 minutes or so, before a final circularization burn that takes us to a 575-kilometer orbit for final payload deployment. Now, there's one part in particular about that launch sequence that will be quite different for our new launch vehicle, Neutron, and that's the fairing in the stage 2 separation. So on Electron, the two halves of Electron's fairing split and fall away, completely ejecting from the vehicle to expose the payload to space, but it's a little bit different for Neutron.
Speaking of Neutron, since our new vehicle is designed for maximum reusability, we've taken a different approach with its fairing. Neutron employs a hungry hippo fairing where the two halves open wide and make way for Neutron's complete second stage plus payload to pass through and continue the mission to orbit. The fairing then closes back up and remains attached to the first stage so the whole system can land back on Earth and be reused. We recently ticked off a big milestone in Neutron's development with the successful testing of this fairing actuation. Let's check it out.
The great thing about Neutron is that we took all the experiences that we had with Electron and rolled that into Neutron. So, a lot of launch vehicles historically have been appended with reusability. We got a blank sheet of paper to start from scratch to make a reusable launch vehicle the way it should be. And you end up with things like not throwing the fairings away and bringing them back down. Yeah, so the fairing stays attached to the vehicle at all times. It's about 6 seconds altogether, so the fairing opens in 1.5 seconds, and then there's a few seconds of the second stage being ejected from the first stage, and then there's about 1.5 seconds for the fairing to close again, and then for us to tip over and head back home. Well, keeping the fairing means that it's much more efficient. You don't have to fish these things out of the ocean, which ultimately drives more cost. There's always a penalty for doing these things. The first stage is slightly heavier coming in and re-entering, but it just means we don't have a refurbishment activity or a recovery activity, and the rocket basically lands exactly as it starts. Yeah, well, the advantage with a carbon composite is that it's very lightweight material. So, it's half the weight of aluminum or 4 times lighter than stainless steel, so for the same specific strength. So it means you can make much, much lighter structures. And ultimately that translates into performance of the vehicle. So the rocket doesn't need to be as big to lift as large a payload. You look at Neutron, it looks quite different to normal launch vehicles. That's because it's optimized to do 2 jobs instead of 1 job. While the rocket has to go up, but equally well, it has to come back down. So a lot of the design decisions are actually influenced by the re-entering rocket, the rocket coming down, rather than necessarily the rocket going up. If you don't have to throw away the fairings and recover them out of the ocean, or you don't have to build them or refurbish them, that's a huge advantage. So keeping everything intact that you don't want to throw away is a great idea. I mean, when a jumbo jet lands, it doesn't jettison its cargo doors. You know, it opens them, and then your cargo goes out, and then you close the door. It's the same principle here.
Can't wait to see the Hungry Hippo in action on Neutron's debut launch soon.
For now, though, back to today's mission, and we would like to take this opportunity to introduce you to a new team member here at Rocket Lab in Mission Control. So meet Alex. He is an avid space fan who let the good folks at Make-A-Wish know that it was his dream to be able to see a rocket launch and to have a tour of our rocket factory. And we were only too happy to help make that happen. It's an honour to have Alex and his family joining us in Mission Control today for launch.
Looking forward to it, Alex. All right, T-minus 3 minutes and counting. And as we approach T-minus 2 minutes, Electron will enter the auto sequence and the vehicle's flight computer takes over. In those final few minutes, you'll hear the various call-outs from Mission Control as final checks and procedures are completed for liftoff. Let's listen in for those calls now.
From now, there should be no red flags on your critical LCCs, VCON, LD, and mission court.
LD VCon.
VCON, lock the auto sequence and confirm.
Locked.
And VCON, confirm all flight computer ASCOs are green.
All flight computer ASCOs are green.
Understood, thank you, VCON. We are go for auto sequence start at T-minus 2 minutes. LD is go for launch.
The vehicle is fully on internal power. FTS is green and enabled for flight.
Box load is complete. System is in recirculation. Anti-geysering is disabled.
Stage 1 and Stage 2 tanks are pressed for flight.
High flow engine purge enabled.
T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Beginning picture.
Stage 1 propulsion nominal.
Okay, the lightning god's reign has begun and we are on our way to space. Electron has lifted off from Launch Complex 1, cleared the pad, and is now travelling at over 800 kilometres per hour as it propels iQPS's satellite towards orbit. Now, one of the next calls you'll hear from our operators is max Q, and that's the point in flight when Electron experiences the highest aerodynamic loads. Let's listen in for that call.
Cleared max Q.
That's max Q behind us, and Electron is continuing its way to space for our 61st mission. Electron is now at an altitude above 17 kilometers, traveling at speeds past 2,400 kilometers per hour. Up next, in quick succession, we have MECO. That's main engine cutoff, which is when the first stage engines shut down. A few seconds later, Electron's first and second stages separate. At this point, Stage 1's role in the mission is now complete. But it's just getting started for Stage 2.
Shortly after separation, the single Rutherford engine on Stage 2 will ignite, and that will propel us the rest of the way to an elliptical transfer orbit. So watch closely to see all of this take place in the next few seconds.
Stage 1 propulsion holding nominal. Stand by for MECO in 30 seconds.
"15 seconds to staging. Enter burnout detect mode.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
And as planned, that sequence of milestones is now complete, and Electron's second stage is continuing to orbit. Now it's the fairing's turn. The two halves of the clamshell fairing will separate and fall back to Earth, exposing the iQPS satellite to space for the very first time. Those fairings, like the rest of Electron's structure, are made from carbon composite, so they're incredibly lightweight but also strong. It's why we're making Neutron's fairings from the same material. But unlike today's fairings, neutrons will stay attached to the vehicle for landing and rapid reuse.
Fairing jettison confirmed.
And there we have it. Electron's fairing has been jettisoned, and the QPS-SAR 9 now has its unobstructed view of its new home in space. We are now coming up to 4 minutes into the flight with less than just a couple more minutes remaining in this second stage burn.
Guidance is nominal.
When it comes to launching rockets and spacecraft, we don't just build, then fly. We rely on rigorous test campaigns to ensure mission success. For new parts, we start with development testing, followed by design qualification, or qual. Qual testing stresses the design far beyond expected conditions it would endure for a nominal mission, with vibration, shock, thermal cycling, and thermal vacuum, or TVAC, being a handful of test examples conducted. Next up is acceptance testing, intended for real flight article hardware. These tests are typically less harsh on components versus qual as to not fatigue them. After all, these are being used on actual mission. The aim is to catch workmanship issues and performance variances. For Neutron, some Electron components are reused but require additional testing due to the high acoustic and vibration levels from the more powerful Archimedes engines. The scope of Neutron's test campaigns cover individual components in isolation up to large integrated tests to ensure various systems, avionics, software, mechanical fluids, propulsion, all work together as expected. That includes tank pressure tests, engine hot fires, and I showed earlier, the hungry hippo.
All right, back to the mission you see on your screen. And next, we are getting ready to hear some of our 4 favourite words: battery hot swap successful. And that will mean that we have reached the point in flight when the depleted batteries that power Rutherford's electric fuel pumps are ejected from the second stage. We then immediately swap over to a fresh set of batteries to get us to the rest of the way to orbit. And that's why we call it a hot swap, since it happens while the engine burn is still underway. So as well as hearing the call out from operators, you should also be able to see the shiny silver batteries fall away from Electron on your screen. So eyes and ears at the ready for that flight milestone.
HGB discharge holding nominal, approaching hot swap in roughly 30 seconds. Throttling down.
Battery jettison confirmed.
Confirmed hot swap successful.
Stage.
Okay, in the eternal words of InSync, we have said bye to those batteries. A fresh set has taken over with just a few minutes now remaining in the flight. And the average orbital Electron mission takes around 9 minutes to reach orbit, which means across more than 60 missions, we have spent more than 9 hours capturing views like this one on our multiple journeys to space. And still, I tell you what, it's a view we never get sick of.
With just over 7 minutes completed in today's launch, we have passed through most of the key milestones with just 2 more remaining. That's SECO, or second engine cutoff, and stage separation. This is where Electron's kick stage separates from stage 2 in preparation for payload deployment. But before that, we've still got a few minutes to watch that Electron's nozzle glow brightly before shutdown.
Okay, T plus 7 minutes, 47 seconds and counting, and everything is proceeding nominally so far. The operators in mission control continue to monitor vehicle systems closely as we approach that all-important throttle down and the second engine cutoff ahead of kick stage separation. Now, if you're keeping an eye on our speed, you want to see that dial at around 27 to 28,000 kilometers an hour, which will indicate that we have hit orbital insertion speed.
HGB discharge holding nominal.
Electron's 61st flight is coming to an end in just a few moments. We're now expecting to hear the call out, burnout detect mode, from mission control. Once we hear that call, you'll know that second stage shutdown is close.
20 seconds remaining.
SECO confirmed.
Nominal transfer orbit achieved.
Stage separation confirmed.
And just like that, Electron's second stage engine has shut down as planned, and the kick stage is now separated to continue the rest of its journey ahead to payload deployment. Now, the kick stage will enjoy a gentle coast around Earth before it reaches its apogee, which is the highest point in its orbit. At that time, the 3D printed Curie engine on the kick stage will ignite and then raise the orbit to a circular one at 575 kilometers above Earth's surface.
Once in that circular orbit, it will be time to wave goodbye to iQPS's satellite as it joins its siblings in orbit. We'll come back for that Curie burn and deployment, but for now, let's take a trip down memory lane and look back at our very first launch for iQPS back in 2023.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
So on that mission, the moon god awakened, but today it is the lightning god's turn. And remember, today is launch number 2 of a total of 9 booked by iQPS on Electron. So many more views like that one are coming up in the next few months and years.
For now, though, let's take a break while the kick stage moves into position for deployment. We'll be back with you in just a jiffy. Welcome back. You're joining us just in time for payload deployment on our 61st Electron mission, a dedicated launch for Japanese Earth imaging constellation operator iQPS. A little over 51 minutes ago, Electron lifted off from the pad at Launch Complex 1. It sailed through 9 minutes of flight before Electron's kick stage entered a coast phase ahead of payload release.
Before then, though, the kick stage has one final task, a circularization burn. And that maneuver will be carried out by our tiny 3D printed Curie engine, which is designed and built in-house by our propulsion team. Now, Curie will raise the kick stage's orbit, moving the kick stage to the precise position as requested by iQPS to deploy their satellite. And that burn is scheduled to begin very shortly, so let's listen in for the call from Mission Control.
Curie ignition confirmed.
Well, that's the call out for a successful Curie engine ignition. This burn will last for around 2.5 minutes before the engine shuts down for payload deployment.
Now, Curie is small and great for missions in LEO or GEO, but back in 2020, we began developing an interplanetary variant of Curie called Hyper Curie. And in 2022, we sent it all the way to the moon on our Capstone mission. And this unit we have here is the qualification unit for the Hyper Curie engine, so you can see the size difference between our regular Curie and this one.
Hyper Curie has about 4 times the thrust of Curie and is optimized for maximum performance, whereas this little guy is optimized for mass production. Curie is pressure-fed, but Hyper Curie is electrically pump-fed, much like our Rutherford engines, and also our proposed Mars Ascent vehicle engine for the Mars Sample Return project.
Curie cutoff confirmed.
Nominal final orbit achieved.
Curie shutdown is confirmed. All that remains now is deployment of iQPS's satellite, and that's Electron's mission complete.
All right, we heard it internally on the nets. Payload deployment is confirmed, and welcome to space QPS-SAR 9. So as we like to call it, that is mission success with that payload now on orbit. Thank you to our mission partners iQPS for launching on Electron once again, and with 7 more missions booked together, we look forward to being on the pad for you again soon.
Well, that's our 61st launch done and dusted. The next launch is never far away, so keep your eyes on our social media channels and websites for details about our next launch, a dedicated mission for return constellation customer Kinéis. Don't forget, if you want to join the team that's making big things happen in the expanse of space, visit rocketlabusa.com and check out the careers page.
And thank you so much for joining us to watch another Electron launch. We love to share what we do with you, and we are so grateful that you are here cheering us on. So until next time, this is Rocket Lab Mission Control signing off.